Hey everyone! Today we are going to be learning about vapor pressure, more specifically how temperature is affected by vapor pressure, which then in turn affects things such as boiling points. So before we can discuss vapor pressure, we do have to learn about evaporation. So let's begin here. Temperature is a measure of average kinetic energy. When we think about an average, we think about having a bunch of numbers that we add up, and then we divide that total number by the amount of numbers that we had. And so you can think about that as each individual molecule is going to have its own temperature. We then added up those individual temperatures of those molecules and then divided the temperature that we have, or the total number, by the number of molecules, and that gives us an average kinetic energy, or temperature. And so here we have a standard distribution curve where the y-axis is the number of molecules and the x-axis is our kinetic energy. We can actually just say that kinetic energy is temperature. So the shaded region here actually represents the number of molecules that are able to escape the surface of the liquid. And this is what evaporation is. So here we have the average of our distribution, and at a given point when we increase our temperature, that's going to cause our molecules to build up enough kinetic energy and leave our liquid. This will then cause our temperature to go down. So this happens when we sweat. So as we sweat, we have molecules that are going to build up enough energy and escape, and that causes our temperature to decrease because we have fewer number of molecules with fewer energy or temperature. So as molecules with the highest kinetic energy escape, that leaves a lower average for those molecules that are left behind. And so as long as moisture can evaporate off, that's why you feel colder or cooler, so that is why we sweat, or why pigs might roll in mud or dogs pant. However, if it gets too humid, the air can't hold any more moisture, and that's why you might feel kind of hot and wet or damp. So how does evaporation relate to vapor pressure? So in this flask here on the left, this is just the molecules at the surface that are evaporating off or coming off, so they have built up enough kinetic energy to leave our system. And so since it is open here, eventually our molecules are going to evaporate all the way off to dryness. So if we left this out long enough without a lid or a cap on it, eventually our water or liquid level would go down. And if we decided to just put a cap or a lid on it, like we see in the diagram on the right, then our molecules don't have anywhere to go. So we have molecules that are evaporating off, but then since they can't leave the system, they'll just condense back down. Condense meaning that they will just turn back into a liquid. So eventually we will get enough pressure in this area here, and we will call that vapor pressure. So enough pressure will build up in our flask, and we call that vapor pressure. So the pressure of the gas that builds up. Alright, so how does temperature affect our vapor pressure? So as temperature increases, so does our average kinetic energy of the particles. So this will actually cause a change in the shape of our distribution curve. So as we said a little bit ago, we said that the x-axis, we could just relate that to temperature. So as our temperature increases, meaning that our graph will go further along that x-axis, then our molecules will actually, more molecules will get enough kinetic energy to leave. So the graph here, or the curve here, this is actually hotter. Whereas the curve up top, where it goes further up the y-axis, but it doesn't go further on the x-axis, meaning it doesn't have more temperature, this is actually a colder or cooler. And so the graph that has the hotter temperature, or is at a higher temperature, it has more molecules that are underneath this curve, which means more molecules are leaving. And because more molecules are leaving, eventually we will feel cooler. Okay. So lastly, we have boiling points. So as we stated earlier, when we have a vapor pressure that builds up, so we have some water here, and we have some evaporation and condensing going on. Here's our lid for our cover. So we will get a build-up of vapor pressure here. However, whenever this vapor pressure, or the area here, equals the atmospheric pressure, or the pressure out here, then that is what is boiling. That is what boiling point is. So boiling point, or boiling in general, is going to be where your vapor pressure, it gets hot enough to equal your atmospheric pressure. So vapor pressure gets high enough to equal the atmospheric pressure, and that will cause bubbles in your system, and those will actually start at the bottom. Whereas before, with say evaporation molecules only leave from the surface, whereas boiling leaves from the bottom. So when we go up in the mountains, or at a higher altitude where our atmospheric pressure is lower, our water will actually boil cooler. So for example, if we went somewhere such as Mount Everest, where our atmospheric pressure, so at ATMP, is lower, our boiling point will actually be lower. And that's because it takes less energy, or less kinetic energy, for our vapor pressure to equal atmospheric pressure. And so somewhere like, say, Mount Everest, we actually get a boiling point of 69 degrees Celsius. Whereas somewhere, say, Missouri, our boiling point in Missouri is actually 100 degrees Celsius. So here in Missouri, we have 100 degrees Celsius. And that's just because we aren't as high up in altitude, so our atmospheric pressure isn't as low. Versus if we go somewhere with higher altitude, or sorry, not higher altitude, lower altitude, so higher atmospheric pressure, so somewhere like the Dead Sea, where our atmospheric pressure is really high, our boiling point is also going to increase. And somewhere like here, our boiling point is actually 176 degrees Celsius. Alrighty, so that's basically all that we have for today. It's just discussing how vapor pressure, or how temperature relates to vapor pressure, which then relates to our boiling points.